Hi, my name is Darryl Peterson and I'm the manager of the Applications Engineering Department. Today I'd like to take a few minutes with you and answer a common question that we get in Applications Engineering, which is, can I shunt calibrate the dummy resistor? And I thought we'd take a few minutes to talk a little bit about what the dummy resistor is and then see if we can calibrate it. And I'd like to draw a sketch for you of a Wheatstone bridge to help answer this question. So I'm going to draw the four corners of the bridge. There's a resistor. And here's another resistor. Here's another resistor to make up our Wheatstone bridge. And then over here I'm going to sketch our strain gauge. So here we've got the active strain gauge. We've got one wire that's going to connect down into that section of the bridge. Another one is going to be a signal output connection. And then the third wire is going to connect down to this corner of the bridge. And if I were to go ahead and draw the power for the bridge, we got the symbol for a battery. That's what's going to electrically power up the circuit. Typically we label this as P plus and P minus. And our signal output connections, this one we're going to call it S plus, and this one is technically out here at the tab of the strain gauge, and we're going to call that S minus. So to answer the question, can I shunt calibrate the dummy resistor, the first thing you need to know is, well, what is considered the dummy resistor? And in this Wheatstone bridge, this location is referred to as a dummy resistor. It's not because it's not as smart as any of these other resistors, it's because it has to change to match the resistance of the strain gauge. For example, if this gauge is 120 ohms, then this resistor has to be 120 ohms in order for this bridge to stay in a balanced condition, assuming that these two resistors are the same. They could be 120, they could be 350, they could be 1,000, as long as these two resistors are the same and these two resistors are the same, the bridge will stay at a balanced condition. Now, shunt calibrating is our method that we talked a little bit about in a previous video, where we simulate a known change in order to produce a known response out of the circuit. This is where we pull our electrical output signal, we'll call it E sub O, and again, this is where we have our input voltage coming in. We can call it big E, or some folks refer to it as V, either one. And what we would like to do is to be able to scale this electrical output so that we can understand what the strain gauge is doing. And in some applications, you may be able to calibrate the device, meaning you take the part that the gauge is on, you put known loads on it, and you calibrate this electrical signal against those known loads. But oftentimes it's very difficult to do. So instead of that, we use this method of shunt calibration to connect a resistor in parallel across another one in order to produce a known change, and we can use that to calibrate our system. So the obvious answer to this is, can I shunt calibrate the dummy resistor? The answer, of course, is yes. Let's talk about how to do it, and let's also talk about advantages and disadvantages. So I'm going to draw a resistor being connected across this one. Typically it has some type of switch. This might be a toggle switch like you see on some of our signal conditioners. This may also be a switch that gets closed with software. And let's assume that the gauge is 120 and this resistor is 120. And I'm going to pick this RCal resistor to be 59,880 ohms. Now the reason I select this resistor at 59,880 is that if I take it and connect it across this resistor, what that's going to do is take this total resistance and it's going to go from 120 when the switch is open down to 119.76. So 120 minus 119.76 equals a 0.24 ohm change. Why is that important? Well, the 0.24 ohms is essentially equal to 1,000 microstrain simulated at a gauge factor of 2. So we pick 59,880, we shunt it across the dummy resistor. We produce 1,000 microstrain of change while we close that switch, and we can calibrate this electrical output for that change. Now, let's talk about advantages and disadvantages. So what's an advantage of shunt calibrating at this location? There's a couple. First, when we calibrate at this location, we cause a total resistance to drop to 119.76. When we're calibrating at this spot, when that resistance goes down, it actually produces a positive voltage out of the circuit. This point stays the same. The voltage here goes down a little bit because that resistance goes down a little bit. This one's higher than that one. That means we get a positive signal out. So I'd say first advantage is that it simulates tension. And if you're primarily testing in tension, then I think that's a good thing. Second, precision resistors. What do I mean by that? This oftentimes is a very precise resistor. If it's not, it should be. Typically, these bridge completion resistors have a tolerance on the order of about 0.01% on their resistance value. And these shunt calibration resistors typically run about 0.1%. So this is a very accurate resistance. This is also a very accurate resistor that we're connecting across it. So I would say you're using precision resistors, which means that you're simulating a very specific level of strain. Third, and sometimes overlooked, is that this method will allow you to compensate for the wire resistance. What does that mean? What it means is this, is that you've got the resistance of these wires. I'm going to label them R sub L of each one. And in this bridge circuit, it's a 3-wire system. We got one wire here, we got another one here, and we've got another one here. This is the wire that's desensitizing the strain gauge because the corner of the bridge is right there. Well, assuming that you cut these 3 wires to all be the same length, we've got this wire that's down in series with this resistor. And this is the one we're shunt calibrating across. So what that means is that this wire is desensitizing this resistor just like this wire is desensitizing our active strain gauge. Is that a good thing? Yes. Why? Because now when we calibrate, it's desensitized just like the gauge is. So what that means is that that allows us to compensate for that lead wire resistance, assuming that we've got a 3-wire quarter bridge circuit, just like we showed. So tension, precision resistors compensates for lead wire resistance. What's a disadvantage? We got all those advantages. Give me a disadvantage. About the only one I can think of is that these cal resistors will have to change as that bridge completion resistor changes. So for example, let's say you look at our instrumentation. Typically we'll have the option for a 120 ohm bridge completion resistor, a 350 or 1000, so you can match 120, 350 or 1000 ohm strain gauges. And because of that, and because we want to keep the simulated strain the same, it means that we've got to have 3 different calibration resistors to connect across each one of those dummy resistors. So what it basically means is that you need more resistors. Now hopefully for you it means that that's already built in by the manufacturer. Not something that you would have to be concerned about, but if you were building your own circuit and you wanted that flexibility like we offer with our instrumentation, then yes, you would have to have more of these resistors built into your circuit. So to go back, can I shunt calibrate the dummy resistor? The answer is absolutely yes. It's our preferred location of where to calibrate. We use this type of method in our strain indicators and our digital data acquisition systems. We calibrate those circuits here at this dummy resistor. Thank you for taking the time to spend a few minutes with me. If you'd like to find out more about shunt calibration, take a look at our website at www.micro-measurements.com. Thank you.